Welcome to Lecture 18 in Aerospace 584 Guidance and Navigation. This is going to be the last lecture on Kalman filters, and we are going to apply Kalman filter finally to the navigation problem in this lecture. So before I start, I want to emphasize the difference between various things that we have been using in the past few lectures. We have been using measurements. We've been talking about measurements, models, and filters. What exactly is the difference between them, and what are the respective applications? So let's consider this simple physical system. We have this little vehicle here. Let me get the pen working. Yeah, we have this physical system, and let's suppose this physical system is described by this differential equation x dot equals f of xu, where x is the state and u is the input. U is the input. And we say that this differential equation x dot equals f of x and u describes the evolution of the state x. It's a mathematical model of this physical system. So let's suppose we could measure all of the state. If we could measure all of the state, then we don't need to rely on this model x dot equals f of xu to get x of t, because we are measuring the whole state. Now in this case, the accuracy is going to depend on the sensors that you have. So if you have poor sensors, you're limited. The accuracy of the estimate of that particular state is going to be limited by the accuracy of your sensor. Now, on the other hand, we have a model of the system. The model is x dot equals f of x and u. And if we know the initial condition x at 0 and the input u of t at all times t, then we can use this model x dot equals f of x and u we can integrate this model, and we can get x of t at all times. Now, of course, the accuracy of the state estimate in this approach is going to depend on the quality of the knowledge of the initial condition, the input, and of course, this dynamics map f, this function f of x and u. If f is asymptotically stable, then your initial condition is not very important, because the effect of the initial condition dies out. If f is unstable, then this approach cannot be used, because any mismatch in the initial conditions is going to lead to divergence of the estimates. And if the function f is what we call as Lyapunov stable, then the effect of initial condition does not blow up, but it also does not go to 0. It lingers on. So that case also is not very useful. So if the dynamics is Lyapunov stable, then we cannot use this approach to get the estimate of state x. And unfortunately, the models that are relevant in this particular course, they're all Lyapunov stable. So this approach is also not very useful. Finally, we have filters, and we have been talking about filters in the last few lectures. And what filters are doing, filtering is basically a framework where if you measure a part of the state x, you have the measurement yt. It's not the full state, but it's a part of the state. And we have the measurement of the input u. We can use the model in this filtering framework to obtain an estimate x hat of the state x. Now, in this case, the accuracy is going to depend on the accuracy of our measurements y and the function f. Okay, let's discuss the main point of this course, navigation. Now, how can we use these three approaches to do navigation? And as you might have seen in the previous lectures, navigation is the process of finding the state of the vehicle. So state of the vehicle includes the position, velocity, its attitude, and its angular velocity. So let's say you have an inertial frame FA. So FA is going to be an inertial frame. We're going to assume that FA is inertial frame. And we're going to assume that FB, this guy, is a body fixed frame. Body fixed frame. And we are going to assume that C is some point fixed in the body, and W is an unforced particle or unforced point, or ZIA point. I don't know if Professor Bernstein has talked about ZIA, but ZIA means zero inertial acceleration. So this is a ZIA point, and ZIA stands for zero inertial acceleration. Okay, so we have a ZIA point, we have a point fixed in the body, we have a frame fixed in the body, and we have an inertial frame. What we are interested in usually is the position of C with respect to W in the inertial frame. Mostly it's going to be the earth fixed frame, and we are going to assume that the earth fixed frame is inertial. So we want the, let me go back. We want the position, we want the velocity of our vehicle, or velocity of point C with respect to the ZIA point in the inertial frame, resolved in the inertial frame. So this is the velocity. Similarly, to describe the attitude of the body, we may be using the Euler angle. So we may want the attitude, and we also want to look at its angular velocity. So if we have all these things, then we know where we are and where we would be going. And then, depending on what we want to do, we'll formulate some control law which would use all this information to get us to whatever the reference trajectory is. So let's see if we can use the just the measurements to do navigation. So like I said, we could use measurements, we could use the model, or we could use a filter. So let's just focus on the measurements. Now, what kind of sensors do we need to make these measurements? So for the position measurement, we could use a GPS. Now, velocity, I don't know. I don't think GPS gives you velocity. So if you have the position estimates from the GPS, you can just differentiate that signal, and then you can get the velocity. Of course, you can do that. And to get the attitude of your body, you can track at least 4 points on the vehicle. So you need 4 points to define a frame. They have to be, you would ideally use 4 points like this. Let's say P0, P1, P2, P3. And if you measure these 4 points, then you can construct like an IB, JB, KB. And then using these three directions, you can get the attitude of the fixed of the rigid body. You could use a mocap system. Mocap is a motion capture system to do this kind of thing, and that will give you the attitude. And once you have the attitude of the system, you can express the attitude in terms of the Euler angles. And to get the angular velocity, you can use this equation that you might have used in the course earlier, where these Euler angle dots are going to be obtained by simply differentiating our measurements. Now, of course, you can do all these things, but it is not the most smartest thing to do. What are the problems in this case? Now, GPS, or the motion capture technology, obviously is very expensive. It's also not very reliable. By reliable, I mean that it takes a while to lock into the good estimates. It's not really available everywhere. If you have a cloudy day, or if you're inside a building, you're not going to have GPS. And of course, motion capture is a lot more expensive. You can't get motion capture everywhere. We have a motion capture facility at EMIR, and you can see it's, if you use it, you'll know how difficult it is to use. And even if you could get all these technologies to get you the measurements, you still don't want to differentiate noisy signals, because if you differentiate a noisy signal, the differentiated signal might have large transients. So this is not an approach that we want to use. No, we will not be using measurements to do navigation. Nobody uses measurements to do navigation. I mean, except very, very simple cases. So the other option is to use the model of the system, and the measurements, simpler measurements. And the simpler measurements are given by inertial sensors. Inertial sensors, Professor Bernstein talked about inertial sensors, the accelerometer and the gyro, rate gyro. These are called as inertial sensors because they measure variables with respect to an inertial frame. So an acceleration measures this quantity, ACWA resolved in B frame. So that's the acceleration of the point in concern with respect to a ZIA point with respect to an inertial frame in the body fixed frame. But the problem with the accelerometers is that they are corrupted by the gravity. So whatever you're going to measure in the whatever your accelerometer is going to measure, it's going to be a combination of the true acceleration and the gravity in the body fixed frame. Rate gyros, they measure the angular velocity of the body fixed frame with respect to the inertial frame in the body fixed frame. So the rate gyro gives you this quantity. And these two are far easier and far simpler and far cheaper than the GPS or the mocap type systems. So these things actually, you know, what you call that thing? 6-axis IMU, they call it 6-axis IMU. I mean, those things are like $5. So those sensors can give you the acceleration in the body fixed frame and the angular velocity in the body fixed frame for like $5. So once you have these inertial sensors or the measurements from inertial sensors, what do? Well, we use a kinematic model to obtain the state. We are, at the end of the day, we are interested in the state. The state is the position, the attitude, and their rates like velocity and the angular velocity. Okay, so we use, you have seen this a million times in your life. The second derivative of the position is the acceleration. And because we want the position of C in an earth fixed frame, so if we differentiate it twice, we get this quantity. Now we don't measure this quantity, but we measure something which is close to this. So we can use this equation with the acceleration measurements to get the position estimates and the velocity estimates. And we can also use the Poisson's equation to get the attitude. The Poisson's equation is this one. You must have seen this earlier in the course. Omega BA resolved in B is the angular velocity that the gyro is directly measuring. This cross is the supercross operator. I'm sure Professor Bernstein must have shown you this, but let me just show you what it is. If you have a vector like this, omega 1, omega 2, omega 3, and you supercross it, you basically get an anti-symmetric matrix with zeros on the diagonal, omega 1, omega 2, omega 3, and omega 3, omega 2, omega 1. And there's a minus here, and a minus here. I'm sorry. So you get a 3x1 vector, you supercross it, and you get a 3x3 matrix. Okay, so we are going to use the double integrator and the Poisson's equation with the inertial sensors to get our state, which includes the position, velocity, attitude, and angular velocity. Now, what are the problems in this approach? Now, in this approach, these two equations, equation 1 and equation 2, they are actually coupled. They don't look very coupled, but they are coupled because we don't actually measure the right-hand side of the first equation. What we measure is this quantity shown here at the top. And the way you relate the two is shown here. So the acceleration in the A frame is equal to OAB times the acceleration in the B frame. OAB is the orientation matrix, where OAB is actually just OBA transpose. So we are going to get OBA from the Poisson's equation, and we are going to transpose it. So anyways, so if we keep going, this is the entity we want, and this is the entity we measure. So we have to invert this whole thing to get the acceleration in the A frame. Anyway, so what we do is we solve the Poisson's equation, and at each time step, Poisson's equation tells you what the orientation is, and using that orientation, we calculate what the gravity is in that frame, and then we use this expression here to get the acceleration in the body fixed, in the inertial frame. Now, the second problem is that both these equations are unstable. Actually, I shouldn't have. Yeah, these are unstable equations. So if you apply an input, let me not get into the definition of stability. I'm going to digress a lot. So both these systems are unstable, which means that if you have any initial condition which you don't know exactly, its effect is not going to disappear. So that, and actually it's going to get worse, because whatever mismatch you have in the initial condition between the true system and your model, the effect of that initial condition is going to grow. And lastly, like every sensor, these inertial sensors also suffer from noise. So these measurements, A of t and omega of t, are going to be noisy. And once you have noisy measurements, your model is, of course, going to diverge from the true system. But we'll discuss that a little more. So let's try to derive the model, or not derive, formulate the model that we are going to use to get the estimates, the position estimates. So let's start with the double integrator. So this is a very simple double integrator. I'm going to use some notation. I'm going to say that the position in the A frame is simply R, and it's a 3x1 vector, and its components are X, Y, Z. So the X component, Y component, and Z component of the position. So what this equation is saying, this and this guy combined is simply this equation. And the fact that I'm measuring the not the acceleration in the A frame, but the acceleration in the B frame corrupted by the gravity, I have to account for that, and I will eventually end up with this equation. Now, this is a second order differential equation because I have two derivatives on R. So I can convert this into, so this is a second order differential equation, second order differential equation. It can be converted into what you call it, this two-dimensional states. Yeah, two-dimensional state space system. We can convert this into a two-dimensional state space system. Actually, this is not going to be two-dimensional. It's going to be six-dimensional because R has 3 components. But anyways, if we convert this into state space, we end up with this equation. And these are our A and B matrices. So we know the A matrix and we know the B matrix. And this is the input that we measure. And this is the state that we always talk about. So if you have the input, we can easily solve this equation. A and B matrices in this system are exactly known. This is not Newton's law. This is not Euler's equation. This is a simple kinematic model, and kinematic model by definition is exact. There is no error in this dynamics. Again, this dynamics is actually a kinematic model, not the dynamics that we use in the usual sense. Okay, so now we have a system which is x dot equals ax plus b times the input. So that's a linear system, and it happens to be an LTI system. So how lucky are we? This is a linear time invariant system, and its solution is very easy. So next we have the Poisson's equation. Now this is a little bit tricky. This is the Poisson's equation. I'm going to call OBA as big Y, and I'm going to write this equation. Now, what is this guy? This guy is simply big omega is simply minus small omega supercross. Now, if you pay attention, small omega is a is a function of time. So my big omega is also going to be a function of time. This is all messed up. So let me write omega t is equal to this. So now, if you look at this equation, this is an LTV system. So it's linear in y, but it's time varying because its coefficient matrix or the dynamics matrix is time varying. So, well, it's not that bad. It's only time varying. It's not nonlinear. So the double integrator by itself is linear. The Poisson's equation by itself is linear. A double integrator is time invariant, but the Poisson's equation is time variant. So we combine these two equations and we get these two equations. Now, the Poisson's equation is independent of the second equation. You can integrate it by itself. But the x equation needs the solution of y right here because we need to get the acceleration in the inertial frame. That's why we need the y. So at each step or at each time instant, you can just integrate the gyro measurements to get the orientation matrix, but that orientation matrix goes back into the position equation. So the whole, both equations combined end up being nonlinear and time varying. Nonlinear because well, the state's not multiplying. Well, the input is multiplying the state because my combined state is going to be x and y, and the input is multiplying y. Input is a, and y is a part of the state. So that's the cause of nonlinearity. And the fact that this omega t depends on t is the cause of time variance. So anyways, these are the two equations which describe the motion, and this is our model. And we are going to integrate this model with the measurements of A and big omega, and that's what's going to give us our state estimate. So let's see how that happens. So typically, these two equations, no analytical solution. I mean, in very simple cases, we are going to have analytical solutions. In fact, one of the examples that I'm going to show you, I'm going to construct a very simple case which has a nice analytical solution, but most cases don't have analytical solutions. So if you don't have analytical solutions, what are you going to do? Well, in that case, we can convert this ODE into a discrete time system using lecture 14 that you guys saw a couple of weeks back. Now, once you convert this into a discrete time system, you can simply integrate or propagate this system recursively on a computer. Now, these matrices AD, BD, and big omega D at step K are going to be, they need to be evaluated. As I showed you earlier, the discrete time AD is simply given by this expression. This is the matrix exponential of A times the sample time. T is the sample time. And A is the kinematic model matrix that I showed you earlier, and I think it was 0I, 0, 0. So A is this. B is given by this expression. I think B was 0I. So these expression can be evaluated exactly, and I'll show you in a second. What about these guys, the Poisson's equation term? So what we are going to assume is that between each time step, we have these time instances, k minus 1, k plus 1. We're going to assume that our omega is a constant. So omega changes like this. So omega, if omega is a constant, then I can assume that between the time step, the propagation is linear. And in that case, using exact discretization technique, the corresponding A matrix or omega D matrix in this case is given by this expression. So exponential of whatever this matrix is. This is what omega T is. And nk hat, n hat at step k is simply the unit vector along the direction of the angular velocity. So what basically we are saying is that we rotate at a fixed angular velocity around the axis of rotation at step k. So think about that for a second. That gives us the big omega d, and using these three matrices, we can propagate our position and velocity, state, and the attitude. Now, AD and BD are constants, and omega dk is going to depend on the angular velocity at each step. So let's see what AD and BD are. So AD, as I showed you, is exponential AT, and A is given by this expression. Now, this is a very special matrix because if you square this matrix, you're going to get a 0. Okay, and I'm going to use that fact to evaluate what e to the AT is. So AD is this guy, and e to the AT is defined as this guy, summation of this infinite summation. And since a square is 0, all that is left is the first term and the second term. And when I add these two, I get AD. So that's a very simple expression for AD, depends on the sample time. Similarly, we can calculate the BD matrix. BD is given by this expression. B is simply 0 and I. So since I know what e to the AT is, I'm going to substitute that expression, actually this expression, into this, and I'm going to get this guy. And when I integrate all components of this matrix, I'm going to end up with this. So AD and BD are very simple. They're just constant matrices which depend on the sample time. So once you have a sample time, once you have selected the sample time, you know what AD and BD are. Okay, so now let's look at a very simple example. Let's suppose we have an airplane which only goes up and down in the IAKA plane. There is no motion in the y direction. Y direction is into the page. YA into the page. Into the page. Okay, so this aircraft only goes up and down in the IAKA plane. So since there is no motion along, there is no rotation about the KB or IB, FB is simply related to FA by the second rotation, and the angle of rotation is going to be theta. This is also called the pitch angle. So this is going to be theta. So since I'm only rotating about the second axis, the omega is going to be omega of B with respect to A resolved in the B frame is going to be given by this expression. The IA component and the KA component are 0, and we only have a component along the second axis. So if this is my angular velocity, which means that I only rotate about the second axis, the orientation matrix at all times is going to be of this form, because I'm only the only angle that changes is about the second axis. So OBA is always given by this expression. So if I know what theta is, then I know what OBA is. Now theta is simply given by this expression, because since I don't have rotations about other two axes, then theta dot actually satisfies this equation. And once I have this, I integrate, I end up getting this. So let's suppose the angular velocity of this aircraft is constant. It's just alpha. In that case, theta is a linearly increasing variable and is given by this expression. So I'm going to consider this very simple case because this allows me to write analytical solution and show you what problems exist in measurement-based or filter-based or model-based navigation. So secondly, I'm going to assume that the acceleration of this aircraft in the B frame is given by this expression, beta 0, 0. This means that the airplane is accelerating in the IB direction. There is no acceleration in the KB direction. There is no acceleration in the JB direction. Now, that doesn't mean that it's going in at a constant angle theta, because theta is increasing. This acceleration is going to keep on changing direction in the A frame, but it's fixed in the B frame. So anyways, when you calculate what the acceleration is in the A frame using the correct orientation matrix, we end up with this expression. So this is the acceleration in the A frame. Now, if we know the acceleration in the A frame, we can simply integrate it twice to get the true position. So our true position is going to be given by this expression. They're both. So the position is going to be a function of both alpha and beta, and this is the exact expression for the position. It includes this harmonic term. There's the initial velocity component, and there's the effect of initial condition. So our position is actually given by exactly this expression. But since this is only true for a very specific case, this is not very useful. So let's look at a more general approach to solving the position and attitude. Well, what we are going to do is we're going to use the model that I showed you earlier. So we have the gyro measurements, and we have the accelerometer measurements. And we are simply going to use the model that I showed you earlier. This is the discretized Poisson's equations, and this is the discretized double integrator. So we know what AD is, we know what BD is, we know what this guy is because we measure omega y at every state, omega at every step, and that is going to give us this expression. And since I'm going to consider omega t equals 0, omega y 0, the axis of rotation at all times is going to be the 0, 1, 0. That's a unit vector along the second axis. And this is also, I write this as E2. So E2 is right here. Okay, so we have the discretized Poisson's equation. We have the discretized double integrator equation. We have these measurements. Our accelerometer is giving us this measurement. And that's all there is to inertial navigation. So using inertial sensors, you get the angular velocity, you get the acceleration, and then you use these two equations to update your state, which includes the position, velocity, angular attitude, and the angular velocity. So let's see what happens when we do this in a real scenario. So let's say our alpha is given by this value. I'm assuming I chose a negative value because I wanted the plane to pitch up because of the choice of my JB axis, which points inwards. I need to have a negative angular velocity to pitch up. So anyways, we consider this case. Alpha is this guy, beta is this guy. I'm going to use a sample time of 0.1 second. The initial value of my state, I'm going to assume that it's it's not a random number, but to show you the case where we don't necessarily know the initial conditions exactly, I'm just going to assume that X0 is just given by this random selection of 6 numbers in MATLAB. So our true initial condition is actually 0, 0. So R of 0, I selected it to be 0, 0, but the model is going to have these 6 random numbers. The gyro error, omega k, is always corrupted by this, and what you call this, the gyro error, and the gyro error, the variance is 10 to the minus 5, so I think it's going to be minus 2.5 because this is squared to get the variance. Similarly, the acceleration accelerometer is going to have the error, so I'm going to have AK plus 10 to the minus 1 omega WK. Okay, so this is omega, and this is W. Okay, so this is what happens. We get this figure here. So this is the true state. Our plane is going slowly up. Actually, this should say Z, because we have motion in the I and K plane, which means you're going to have motion along the x-axis and the z-axis. So this is the true state, and this is what our inertial navigation system provides us, because we have initial error, we have gyro errors, and we have the accelerometer errors. if we integrate the two equations that I showed you for xk and yk, this is sadly what happens. This is a huge error. After, I think I ran it for 10 seconds. So in 10 seconds, you're off by almost 2 meters in the y direction and roughly about 5 meters in the x direction. So, well, this may be good or bad depending on what you're trying to do, but this in this figure looks really bad. And these errors are due to the discretization scheme that we chose, sample time we chose. Our initial conditions were not very good, so that's one of the problems. And we have the errors in our measurements, so that's a problem. These three problems combined make inertial navigation problematic. But it's not that problematic, because if you were to use really better sensors and much smaller time steps, so our time step is reduced, our initial condition estimate is improved, and our gyro is now 2 orders of magnitude better. Our accelerometer is 2 orders of magnitude better. Now, of course, all these things are going to require a lot of money, because you have a lot more computational load. You need to get the initial estimate correct. Your sensors are going to be more expensive because they are, of course, their variance is smaller, they are better. And immediately you see that our estimate is a lot more closer to the true value. So this is the same case that I showed you earlier. The red one shows the true, and the blue one shows the inertial navigation estimate. So if you have better sensors, inertial navigation actually gives you an estimate which is very close to your true solution. And that's what inertial navigation is. It uses only the inertial sensors which give you the input to the model. The model includes the double integrator and the Poisson's equation. So model is equal to the double integrator plus the Poisson's equation. And your measurements are the inputs. Measurements are not the states, as usually they are in, when you study linear systems or such subjects. You assume that the measurements are some component of the states. But in this particular case, in this particular application, inertial navigation or navigation, the measurements are the acceleration and the angular velocity, which end up being the inputs to the model, which is the double integrator and Poisson's equation. Okay, so now we have been yapping about Kalman filter for the last few lectures. So can we use the Kalman filter in this particular application? So let's see. So let's first focus on the Poisson's equation. So this is the model of that we are using to propagate the attitude. Now I'm going to write this in the KF framework. In the Kalman filter framework, I replicate the dynamics. There is no B term. In fact, the A term is the input. So this is the dynamics. And again, I'm going to put this in quotes. This is not really a dynamics. This is just a kinematic model. And we have the measurements of the angular velocities. So omega k, actually AK is a function, is some function of omega k. And you see in the previous slides what that function is. Oh, I'm sorry, I have it right here. I didn't see. So AK is given by this expression. This is a nonlinear function. Now, what does a Kalman filter do? Kalman filter has a copy of the dynamics, this equation, which we call the I forgot what I called in the last lecture. I think I called it the physics update. So this is the physics update, and this is the data assimilation step or measurement assimilation step. So what does the physics update do? Physics update basically copies, uses the dynamics of the system to put our posterior at step k to prior at step k plus 1. And then we combine the measurements and we update the posterior at step k plus 1. Now, we need the output error. So output yk plus 1 does not depend on the state. It's only the input. Now, if this is the input, this is what we measured, what is going to be the output, corresponding output in our estimator? Well, that's going to depend on the prior state estimate. But as in this case, the measurement does not depend on the prior on the state at all. It only depends on the input. So whatever I'm going to write, so I'm going to write whatever corresponding output of the prior state estimate equation is, which also happens to be omega k plus the noise. So omega k plus the noise is exactly what yk plus 1 is. And since both of these quantities are equal, this whole thing actually ends up going to 0. So we are left with just this equation, which means that when we try to apply Kalman filter with the gyro, rate gyro as the measurement, the Kalman filter does not affect the posterior or the prior state at all. We just end up getting the simple integration of our kinematic model back. Okay, so that's what happens with the Poisson's equation. Let's look at what happens with the double integrator. So this is the discretized double integrator. I'm going to write down the model again in the Kalman filter notation. So our state X is propagated by this equation. We know A, we know B. Okay, so I'm going to, since GA is the gravity in the A frame, which we know, this is a known input. So since this is known, I'm going to just write it like this. I'm going to write this guy as BK times UK. So this is UK, and this guy is BK. And then since we might have errors in A of K, well, we actually do have errors in the accelerometer measurement. So we're going to have this term BK times WK. In this case, the output again is the accelerometer, which is corrupted by noise. So AK plus D2 times WK. WK is the white noise. And as before, we are going to construct the physics update, which takes the posterior, produces the prior. It's going to include the original dynamics, the constant input, and the measured input. And again, the posterior at k plus 1 is obtained by the data assimilation step. And again, we are going to look at the output error. The output is the measurement. Output is the accelerometer plus the noise. And what would be the output of the estimator? That actually also is the same, because we don't have any component of the state which affects the state. So this again is going to give me a 0. And again, I'm going to be left with this equation, which means that the Kalman filter does not affect the model. So the point is, if you're using inertial sensors, just AK and omega K measurements, Kalman filter is not even applicable, because whatever output you want to use in the Kalman filter, make the output error 0. And when you multiply 0 with anything, you get a 0. So you never get the correction step. You only get the physics update. And there is no data assimilation step when you're doing inertial navigation. So to use Kalman filter, we really need a state. We really need a measurement, which includes a component of the state. Okay, so what technology is going to provide us that measurement? Usually it is the GPS. So Global Positioning System can provide you position measurements, and it uses the position fixing method. The way it measures the position is irrelevant. You've seen it in the previous lecture. The fact is that GPS provides you position measurements, but they're not very good. The accuracy is no better than 5 meters. The sampling period is not constant. I don't know exactly how GPS works, but I know that GPS doesn't update at a constant time steps. It is affected by a lot of factors. Anyways, the way we model these measurements is by this equation. So yk is now going to be, I'm sorry, is now going to be the position component of the state. So our state was, if you remember, was r, sorry, not, I don't think I can use, let me, so our state was the position and the position dots sampled. So this matrix C equals I0 is going to pick up the position component of this state. So this is the model of our GPS. So GPS measurements are basically the position plus some error. D2 is going to depend on the accuracy of the GPS. Now again, what we are going to do is we are going to use the dynamics that we saw, which were the discrete time, discrete integrator, double integrator, and the Poisson's equation. That's our dynamics. We're going to use those two equations to update the state in between the GPS measurements. I forgot to say GPS. And when the GPS measurements are available, we'll use the Kalman filter to do the assimilation step, or which corrects the state. And we'll see how it corrects the state in a simple example. So let's revisit our previous example. We have this airplane which goes up and down in the IAKA plane, rotates about the JA axis. I'm going to assume that we have a constant angular velocity, so I know exactly what theta is. So this allows me to calculate the true orientation and thus the true position. I'm also going to assume that the acceleration is along the IB axis in the body fixed frame. You've seen this, that this ends up giving me this as the acceleration in the A-frame. But anyways, this is not used in the Kalman filter application. These two equations are only used to construct the true solution, which allows us to see the errors. Anyways, so we have the Poisson's equation exactly as before. We do not have any measurement of the attitude, so there is no output to merge, but we have some estimate of the positions available using the GPS, which can be merged with the dynamics model of the state, position, and the velocity. So big X is the position and the velocity, and now our measurement is going to be the position given by GPS, and that position ends up being this component of this state. So that's the first three components of the state, I times R and 0 times R dot. Okay, so that's the model that we are going to use with the Kalman filter. And what does Kalman filter do? So like I said, no attitude measurements. So we're not going to apply Kalman filter to the Poisson's equation. We are only going to apply KF to the double integrator. Okay, so we have the double integrator equations, and then we propagate these equations at each time step, and then we look at our GPS. If there are no GPS measurements, then we just accept the state update using this equation. Our posterior is equal to prior because there is no measurement. And if there is a GPS measurement, we are going to use the Kalman filter gain along with the output error, which is the difference between the GPS measurements and our model predictions. So that's going to give us the output error, and we're going to use that with the Kalman gain to produce a better estimate of our state. So this is the correction state, which happens only when GPS measurements are available. So let's see what happens. So I'm going to consider the same case that I did before. Alpha and beta are exactly the same as before. And I'm going to show you the poor inertial navigation case, the one where we had really bad estimates. So this was obtained by the inertial navigation, where we just integrated our measurements. We have the same poor gyro, poor accelerometer, bad initial condition estimate, poor computer, which only allows 0.1 seconds of time step. And now, so the red shows the true trajectory. Again, these are supposed to say Z. And this green guy is what is produced by the GPS navigation. So what's happening here is that the GPS values which are available, oh yeah, I didn't say. So I'm assuming that GPS is available every, I think 6 or 7 seconds. I will have to check. No, GPS is available every 1 second. So YK is available, I didn't mention that in the slide, available every second. So every second, so between every second, we have 10 of these sample times. So for 9 steps, we are going to use the dynamics, and at every 10th step, we are going to assimilate the GPS measurement. So this is the GPS measurement. So the top figure shows all 3 trajectories, and this one shows the zoomed in case. And you can, so we don't see the inertial navigation now. We see the GPS navigation, and we see the true. So you can see that the GPS based navigation actually reduces the error a lot. We are very close to our true trajectory. So like I've been saying, any filter, actually Kalman filter, let's just stick with Kalman filter. Kalman filter can take your original dynamics and partial state measurements to improve the accuracy of your state. And it's a very powerful technique to optimally estimate states. So that's it. Like I said, Kalman filter provides a mechanism that we can use to use with the measurements to improve the accuracy of our state estimates. And KF, usually the usual application of the Kalman filter is to produce the estimates of unmeasured states. But like I showed you in last couple of lectures, if you use Kalman filter even for the measured states, Kalman filter ends up improving the accuracy. So it's useful for both the measured and unmeasured state. Now, as far as inertial navigation goes, Kalman filter, unfortunately, is not useful because we don't have the measurement of any component of the state in inertial navigation. Inertial navigation purely depends on the quality of your sensors and available computational resources. So the better initial condition estimates, the better sensors you have, the faster you can run the model, the better your inertial navigation is going to be. But for applications where GPS or any other position measurement is available, we can apply Kalman filter. And of course, since Kalman filter is fusing the measurements with the same model that inertial navigation uses, its estimates are definitely going to be better than just the inertial navigation. All right, so that is it. That's all for my lectures. Professor Bernstein will be beginning his lectures on guidance, I suppose, next week. Please, if you have any questions or I made any mistake, just email me and I'll try to get back to you as soon as possible. Thank you.